First we'll look at the operator called inverse operator. We have taken d as the operator which was denoting for the differentiation d by dx. Here the operator 1 by d denotes integration. D inverse or 1 by d is called inverse operator. So 1 by d q of x is integration of q of x dx. If I write 1 by d square q of x, then that is nothing but double integral q of x dx dx. There d was representing differentiation with respect to x. Here 1 by d represents integration with respect to x. Particular integral or particular solution. Particular integral doesn't contain any arbitrary constants. If given differential equation is f of d into y is equal to q of x, non-homogeneous linear differential equation, then only we'll have particular integral. So if the given differential equation is of the form f of d into y is equal to q of x, then ypi will be 1 by f of d into q of x. When you are given the differential equation like this, ypi we are writing that as 1 by f of d into q of x. This f of d, as we already discussed, that this can be written as a product of n factors. Product of n factors. Like ypi, I can write it as 1 by d minus a1, d minus a2, d minus a3, so on, d minus an into q of x, where that a1, a2, n3, so on may be real or complex. Then I can separate them by using partial fractions, and I can write them as 1 by d minus a1 into q of x a times, or else I'll write this a by d minus a1 plus b by d minus a2, or a1 I'll write this as a2 d minus a2 plus a3 d minus a3 plus and so on an d minus an into q of x, right? Ypi we are writing that as 1 by f of d q of x. Then that f of d can be expressed as the product of n factors. So I am writing them as n, that is d minus a1, d minus a2, d minus a3 and so on. Then by using partial fractions, I am writing that as a by d minus a1 or a1 by d minus a1 plus a2 by d minus a2 plus and so on an by d minus an into q of x, right? Then I'll separate the terms. Then I'll write it as a1 by d minus a1 into q of x plus a2 into 1 by d minus a2 q of x plus and so on an 1 by d minus an into q of x. I'll write this as equation 1. Alright? General formula for calculating particular integral. 1 by d minus a q of x. Ypi is equal to 1 by d minus a into q of x. If f of d is of the form d minus a, then ypi is equal to 1 by d minus a into q of x, which is equal to e power ax integration of e power minus ax into q of x dx. How we are getting this formula? This is the general rule for calculating the particular integral. This can be applied for any q of x. It may be sin x, it may be cos x, it may be hyperbolic functions, it may be exponential functions, or it may be a polynomial and so on. This is the general formula for calculating the particular integral for any q of x. But this will be little bit lengthy, so that the reason we'll be using the particular or the direct methods for q of x as exponential function, trigonometric function, sin ax, cos ax, polynomial and so on. Apart from those, if we have any other function as q of x, then we'll be using this general formula for calculating the particular integrals. Okay. Now we'll see how we are getting this particular formula 1 by d minus a q of x as e power ax into integration of e power minus ax into q of x. Consider 1 by d minus a into q of x and let it be equal to some y, because we are calculating this one. So I'm supposing that let it be equal to some y. Then if I rearrange it, I'll get that as q of x is equal to d minus a into y. I'm supposing this as y. Okay. So q of x is equal to d minus a into y. Then I can write this as dy by dx minus ay is equal to q of x is clearly a linear differential equation in y with p equal to minus a and q is equal to q. In place of a p, I have minus a and q is q. Right? Then the general solution is y into integrating factor is equal to q into integrating factor dx plus c. But as we are discussing the topic particular integral or particular solution, we know that it doesn't contain any arbitrary constant. So therefore I won't use any arbitrary constant over here. So integrating factor is e power integral p dx. Then that becomes e power integral minus a dx, which is equal to e power minus ax. Y into e power minus ax is equal to integral of q into e power minus ax into dx. Then y is equal to e power ax. I'll send this term the other side. Then that becomes e power ax integration of q of x into e power minus ax into dx. But what is y we considered? That is 1 by d minus a into q of x. If you observe the consideration what we have taken, that is 1 by d minus a into q of x as some y. So I got the y. So I'll write that as 1 by d minus a into q of x, which is equal to e power ax q of x e power minus ax into dx. Using this formula in equation 1, we can calculate particular integral easily for nth order linear differential equation, right? For each term we can use this particular formula and we can calculate the particular integral easily, right? Now we'll see one problem based on this, then we'll move on to the special cases, that is exponential, trigonometric sin ax cos ax and polynomials, and the fourth case is e power ax into v of x, and the fifth case is x into v of x. Leaving all these cases, if you are given q of x, you have to use general rule for calculating the particular integrals. Problem 1. Solve d square plus a square into y is equal to tan ax. Finding the complementary function is the same as what we have done in the homogeneous differential equations. Only for finding the particular integral, we have to apply the conditions what we have written just now. So in the this is a non-homogeneous linear differential equation. Given d square plus a square into y is equal to tan ax is a non-homogeneous linear differential equation of the form f of d into y is equal to q of x, where f of d is equal to d square plus a square and q of x is equal to tan ax. So for finding the complementary function, first we should consider only the homogeneous differential equation, that is d square plus a square into y is equal to 0. Then for finding the particular integral, we have to use the conditions what we have written. For finding complementary function, consider f of d into y is equal to 0. You have to consider only the homogeneous differential equation, that is d square plus a square into y is equal to 0. Right. Here f of d is d square plus a square. Now write auxiliary equation. Applying the same technique, f of m is equal to 0. Then this implies m square plus a square is equal to 0, or m is equal to plus or minus ai. Again, the roots are complex of the form alpha plus or minus I beta. So I'll write this as m is equal to 0 plus or minus ai. So this is of the form alpha plus or minus I beta, where alpha is 0 and beta is a. So therefore I can write YCF is equal to e power alpha x into c1 cos beta x plus c2 sin beta x. Then this is equal to e power 0x into c1 cos ax plus c2 sin ax. This is YCF. This is only one part or one solution of the non-homogeneous linear differential equation. We have to find out the other part, that is particular integral. Then the combination of the two will give you the general solution. Then we got YCF. Now we'll find out YPI. YPI is equal to 1 by f of d into q of x, which is equal to 1 by d square plus a square into q of x, and that is tan ax, right? I told you that whenever you are given f of d, split them into factors and separate it and try to use the general rule for evaluating or for calculating the particular integral. So I'll write this as 1 by d plus ai into d minus ai into tan ax. Then we can write this as 1 by d minus ai minus 1 by d plus ai into tan ax into something, right? Write the smaller term here and the bigger term here. If you take minus sign or plus sign, by trial and error you will have the terms like this. If you observe here, I'll get d plus ai minus d plus ai by d minus ai into d plus ai, if I solve this here. So my d will get cancelled. I'll get 2ai. Do I have here 2ai? No. So I'll multiply and divide by 2ai. This 2ai into this, I can write like this. And whatever the division I have done, that will be as it is outside. Yes? What I am doing is, I am multiplying and dividing by 2ai, 2ai. This 2ai by this, I can write it as this inner part. And whatever I have written 1 by 2ai, that will be as it is. Or else, you can also apply partial fractions. You can write a by d plus ai plus b by d minus ai, and you can find out the values of a and b, which you will get that as 1 by 2ai minus 1 by 2ai. So this is the direct method or the shortcut for separating these two terms in this way. Then I can write this as 1 by 2ai 1 by d minus ai into tan ax minus 1 by d plus ai into tan ax. I'll write this as equation 1. If you observe, this is of the form 1 by d minus a into q of x, right? We know that 1 by d minus a q of x is e power ax integration of q of x e power minus ax into dx. By using this formula, we have to calculate these two values, or we have to evaluate these two, right? So now I'll consider the first part. Consider 1 by d minus ai tan ax. Then that will be equal to, see that in the place of a you have ai, in place of q of x you have tan ax. So I'll replace them here and I'll get that as e power aix integration of q of x is tan ax e power minus aix into dx. Then this I can write it as e power aix integration of tan ax. Tan ax I can write it as sin ax by cos ax. If you observe, I have the other term as e power minus IAX. We know that e power I theta is cos theta plus I sin theta. So I'll get the terms in terms of cos and sin. So I'll write that as cos AX minus I sin AX into dx. Since e power I theta or e power minus I theta is cos theta minus I sin theta. So with this, we are able to separate like this. So we can write e power AIX integration of. Now we'll multiply these terms. We'll get that as sin AX cos AX by cos AX minus I into sin AX by cos AX into dx. Then this we can write it as e power AIX integration of. This and this will get cancelled, and here we'll have sin square by cos. So we can write it as sin AX minus I into sin square AX by cos AX into dx. Since the numerator is in terms of cos, then sin square should also be expressed in terms of cos. We know that sin square x is 1 minus cos square x. So we replace sin square with cos square, that is 1 minus cos square. So this I can write it as e power AIX integration of sin AX minus I into 1 minus cos square AX by cos AX into dx. Then again solving it, we get that as e power AIX sin AX minus I into 1 by cos is secant AX minus cos square by cos. I'll get that as cos AX into dx. Then integrating this, I'll get that as 1 by d minus AI into tan AX is equal to e power AIX. Integration of sin is minus cos AX by A minus I into integration of secant AX is log mod secant AX plus tan AX divided by A minus integration of cos is sin, so sin AX by A. This is 1 by d minus AI into tan AX value. So I'll write this as equation 2. Similarly, I can write what is d plus AI into tan AX. D minus AI, d plus AI. I can get d plus AI value, that is 1 by d plus AI into tan x value, just I with minus I in equation. Replace I with minus I in equation 2. So we get that as 1 by d plus AI tan AX is equal to e power minus AIX into minus cos AX by A plus I log secant AX plus tan AX with mod whole divided by A minus sin AX by A, this as 3. Substitute 2 and 3 in equation 1. Equation 1 was YPI is equal to 1 by d square plus a square tan AX, which we wrote that as 1 by 2AI, 1 by d minus AI minus 1 by d plus AI. We calculated both the values, so we'll substitute them here. E power AIX into minus cos AX by A minus I by A log secant AX plus tan AX, then plus I by A sin AX, then minus. We have to substitute this value, e power minus AIX into minus cos AX by A plus I into log secant AX plus tan AX or I'll write here I by A log secant AX plus tan AX. Then here also I'll multiply it. So minus I by A sin AX. Now we have to solve this very carefully. So 1 by 2 AI. Now I'll take first term of these two brackets. I can write it as minus cos AX by A. If I take out, then I'll have e power AIX. I've taken these two terms common. Then this minus this will be there, e power minus AIX. Then take out common term, minus I by A this term, log secant AX plus tan AX, common, minus I by A this term I'm taking out common. Then I'll get that as e power AIX. Here also I took out common, so I'll have only plus sign. So e power minus AIX. Then I'll see the third terms, plus I by A, and here also I'll have plus I by A. So I'll take out plus I by A sin AX common. Then I'll have e power AIX, and here also plus e power minus AIX. E power AIX plus e power minus AIX. And we know that e power IAX plus e power minus IAX by 2 is cos AX, and e power IAX minus e power minus IAX by 2i is sin AX. So we'll replace these two in the above. Then we get that as minus cos AX by A square. I'm taking that 2i inside that. So I'll get that as e power IAX minus e power minus IAX by 2i. Then minus I by 2ai 2a square I into log secant AX plus tan AX into e power IAX plus e power minus IAX. I'm sending this to here so that I can write that in the form of sin and cos AX. Then plus 1 by A square I by A square I. I'm taking 2 inside the bracket, sin AX into e power IAX plus e power minus IAX by 2. I'm keeping A terms and I terms outside in these two terms, and I'm sending 2 inside. And here I'm keeping 2i term inside and the remaining terms outside that bracket. So this will become minus cos AX by A square, and this we know it is sin AX. And here I will get cancelled. We'll get that as minus 1 by A square log secant AX plus tan AX into e power I theta plus e power minus I theta by 2 is nothing but cos. So we'll get that as cos AX. And here also I got cancelled. So we get that as 1 by A square sin AX into, and this becomes cos AX. Right? If you observe, the first term and the last term are same with minus sign and plus sign, so they get cancelled. So therefore we get ypi is equal to minus 1 by A square cos AX into log mod secant AX plus tan AX. This is ypi. So therefore the general solution is given by y is equal to ycf plus ypi. And ycf what we got is e power 0x c1 cos AX plus c2 sin AX plus the particular integral ypi, we got that as minus 1 by A square cos AX log mod secant AX plus tan AX. This is the general solution.